Hello, thanks so much for coming to my lecture, Glass for a Sustainable Future. My name is John Mauro, and I'm a professor of materials science and engineering at Penn State University. First, I would just like to say thank you to the American Ceramic Society and to Darshana and Arun Varshneya for awarding this Frontiers in Glass Technology lecture. This means so much to me because Dr. Varshneya, of course, was my advisor from Alfred University and my glass guru. I have learned so much from him and taken so much inspiration in both glass science and in glass technology, but more importantly, as an advisor and as a mentor for future generations of students. So everything that he has taught me about how to be an effective professor and how to put students first, this is something that I am trying my best to live up to. And so I just wanted to give my deepest thanks to the Varshneyas and to the American Ceramic Society for all of my friends and colleagues there. I hope you enjoy this lecture on Glass for a Sustainable Future. What I would like to do is to give you a little bit of background about my own journey in glass that led me to where I am now at Penn State. I'd like to give you a brief introduction to what we're doing in our glass research group at Penn State, and then I will spend most of the lecture talking about some of our recent research in LionGlass, including some of the latest developments, such as our first ever pilot scale trial. Here is a LionGlass cup that is fresh from Venice. So this just came back from a trial that two of my students went there together with our partner Bormioli Luigi and did a really nice job making these LionGlass cups. So I will tell you more about that in the latter part of the lecture. So first, a little bit of my background. I grew up in upstate New York in the southern tier, about 50 miles from Corning. And I first fell in love with glass when my parents took me to the Corning Museum of Glass. I was just 6 years old, and I fell in love with the beauty of this material, all the different colors, all the different shapes. I love to watch the artists working, especially the flame working, and I really just wanted to see every single piece of glass in that museum. I didn't realize that it was a valid career choice until I saw this great video from Alfred University called What is Ceramic Engineering? Everything just came together for me, and I went to Alfred to do a double degree, a BS in glass engineering science and a BA in computer science, working, of course, with so many great professors, most of all my advisor, Dr. Varshneya. Alfred provided me the perfect environment for learning about glass, and they did such a great job with glass education. From there, I went to Corning Incorporated. I actually started there as an intern and then joined full time. They sent me back to school at Alfred University, where I got my PhD in glass science. I stayed a total of 18 years at Corning. I had kind of a balance between working in the fundamental science of glass and then applying that science toward the design of new glass compositions and a deeper understanding of existing commercial glass compositions. When I first started at Corning, this was during the big fiber and photonics boom, and I was working in optical fiber. I was working on developing new models for the propagation of optical signals through different types of optical fibers, and then trying to use those models to help optimize the design of fiber optic communication systems and networks. I was in the modeling and simulation department while working on this. I was in that department for 11 years. From there, I started to work in the glass research department. I spent a lot of time on fundamental glass physics, including fundamentals of glass transition and relaxation behavior. This was especially important for Corning's display glasses, these very thin sheets of glass that are used in flat panel displays. Relaxation behavior is the single most important property of these glasses because as the resolution improves in displays, the pixel size becomes smaller and smaller, which means that there are tighter tolerances to any dimensional instabilities. So I spent many years developing new models for viscosity and relaxation behavior. Our Maega model for the viscosity of supercooled liquids and the MAP model for the non-equilibrium viscosity of glass were both developed as a part of projects that I was working on for Corning Display Technologies. I also spent many years working on Corning Gorilla Glass. This included developing new models for composition dependence of Gorilla Glass properties and applying those towards the design and optimization of commercial Gorilla Glass compositions. I got to work with so many great people on both the experimental and modeling side, and all the way from fundamental research through development, through engineering and legal departments. And it was just a great experience to be able to take something that is just an idea that is, in a spreadsheet on my screen and then go all the way out the door with a commercial product and see it adopted by billions of users worldwide. Now, while I was at Corning, I was also serving as one of the primary interfaces between the company and the academic glass community. And in my latter years at Corning, I was also the senior research manager of the glass research department there. And we were becoming increasingly concerned that it was difficult to find well-qualified students to hire in glass science. A lot of the professors that I had learned from, or my colleagues had learned from, were retiring, and they weren't necessarily being replaced by new glass professors. And we were also finding that a lot of the glass research that was being conducted in academia wasn't necessarily good training for industrial jobs. There's a lot of work going on, for example, in metallic glasses. Which is, very interesting, but it's actually not the best preparation for industrial glasses, which are overwhelmingly oxide glasses. So we did some studies here to see how the number of glass publications was evolving in different countries as a function of time. I worked closely together with Professor Edgar Zanotto on this, and we've got a nice paper together. But this is showing that in the United States, US was on top in terms of the number of publications in glass science for most of history up through the 1990s. And then we kind of flattened off there and, even had maybe a little bit of a decline in recent years. And it was a similar story in Japan, which showed an even bigger decline, and some other countries in Europe that were traditional powerhouses in glass, like the UK and France and Germany. At the same time, China started out with nothing here in the 1960s, and then their growth has been just about exponential over time, and they have invested a lot in glass research. They have been doing an amazing job developing their groups there, doing great research and publishing a large number of high quality papers. And as of the time of this publication, they were about doubling the output of the US. And so we were, concerned here in the US about where we were going to, hire the next generation of glass scientists. So we decided to do whatever we could to try to stimulate the academic glass research community. We organized a series of Corning Glass Summits where we brought together the professors in the US who were working in glass, representatives from funding agencies. We emphasize that there's still so many great topics for academic research in glass science, and try to do our best to encourage that. But then we found out that Professor Carlo Pantano at Penn State was planning to retire, and we got even more concerned because we had hired every single one of his students for like the past decade, and they were just all wonderful contributors to Corning. I worked closely with a number of them, and there was no guarantee that that position would be replaced by a glass person. So anyway, to cut a long story short, my former boss from Corning told me that I took the problem a little bit too seriously when I quit my job there and applied for the position and took the job as the next professor focusing on glass science here at Penn State. And it turns out it was a wonderful move. I'd always heard such great things about Penn State and about the state college community from all the Penn State graduates that I'd worked with at Corning. And all those stories are true, and it's even better than we could have expected. What we found here is just a wonderful community at all levels in our Department of Material Science and Engineering, our College of Earth and Mineral Sciences, Penn State University, and the Happy Valley community. It's just been a phenomenal experience for all of us. And it was a really special delight for me to welcome my advisor, Dr. Varshneya, to campus the year after I came here to organize the University Conference on Glass here at Penn State. And it was just a great moment for both of us. And I want to point out that since then, the Varshneyas, Darshana and Arun, have very generously endowed this conference series, the University Conference on Glass, now known as the Varshneya University Conference on Glass, going forward, so that this conference, can go forward without having to worry about how we're going to get funding to make this happen. And another really special moment for me was last year. Actually, two of my former students, Colin and Rebecca, who are now at Alfred University, organized the Varshnea University Conference in Glass at Alfred, and I was able to bring most of my group from Penn State to my hometown and show them around the beautiful campus and see what great work that Colin and Rebecca are doing at Alfred. And that also means that I have academic grandkids now, my students having their own students, which makes me feel both old and also very proud of everything that they're doing. Next, I'd like to give you a brief overview of what we're doing in my group here at Penn State. We've got a really comprehensive group in glass science covering everything from basic theory and computation all the way through experimental glass melting, the design of new glass compositions, characterization, and so on. And Dr. Maziar Montazerian here, I'd like to give a big thank you to Maziar. He is the assistant research professor in my group and has been leading the charge on a lot of our research related to glass ceramics, bioactive glasses, and crystallization. He's also been a wonderful mentor for many of the students in my group. Also, a big thank you to Dr. Hongyan Kim, who is a postdoctoral scholar who is leading a lot of our research efforts on modeling and simulation. He has done so much great work on molecular dynamic simulations of glasses, density functional theory, machine learning, especially of glass ceramics as well. And he's also been a wonderful mentor for my students who are specializing in modeling and simulation. And another huge shout out and thank you to Dr. Nicholas Clark. I feel like I've known Nick since he was a kid because when I first came here, he was an undergraduate student working with Carlo on glass dissolution behavior. He stayed and did his PhD with me on phase separation in glass and then stayed on as a postdoc. And he is now leading our experimental efforts on LionGlass. And he has learned so much and grown so much, and also just been a wonderful mentor for both PhD students and undergraduate students who are working in LionGlass. And everything that I'm going to show you in the latter part of this presentation comes back to Nick and the students working in LionGlass. So I just wanted to give a huge thank you to him as well. I've got two new postdocs joining the group who are both the latest PhD graduates from my group. Dr. Brittany Hawkey here on the left. I first met Brittany when she was a student at Coe College, an undergraduate student there, and she was selected as our Stookie intern at Corning. So we worked in the same group at Corning, and she went to do her master's degree at Arizona State University, and then joined my group as a PhD student, focusing on calorimetry of glass, glass relaxation behavior, and glass chemistry. She's also an artist and does amazing work combining science and art. And she's going to stay in the group as a postdoc. And also Dr. Titus Reed over here on the right, he served in the U.S. Navy for 8 years and then came back to school to get his PhD in material science and engineering, working on cementitious materials. And he has been focused on LionGlass for the past year. And together with Nick, leading the effort with Bormioli Luigi, doing phenomenal work on understanding glass chemistry and how that glass chemistry influences properties. And Titus is also staying on for a postdoc to continue his great research in LionGlass. So congrats to both Brittany and Titus for their PhDs, and thank you to them for staying on as postdocs. We have a number of current PhD students in the group. Elif has experience in the Turkish glass industry. She worked at Şişecam there, and her PhD is focused on LionGlass, particularly with respect to recycling of LionGlass and cullet compatibility. I'll be speaking a little bit about her research later. Everything that I'm going to tell you about LionGlass recycling and cullet compatibility is Alif's work. Shaylee was actually an undergraduate student here at Penn State. The first time I taught my Intro to Glass Science class, which, by the way, now has this textbook, Fundamentals of Inorganic Glasses, third edition. First author is Dr. Varshneya. Second author is myself. But Shaylee was in my first ever glass class. She went out and got 3 years of experience in the polymers industry and then came back to Penn State to get her PhD. She's focused on polymer coatings on glass, so building upon her dual expertise in polymers and in glasses. Then there's Arun Bosson. Arun got his degree in both bachelor's degree and master's degree from University of Wisconsin at Madison. He has background in metallic glasses. He's also a glass artist. He is managing our glass studio in the next building over here. He's very passionate about STEAM pedagogy, science, technology, engineering, and art and mathematics. He is this wonderful bridge between the scientific and the artistic communities. He's also leading the charge on some of our basic theory of glass relaxation and glass transition range behavior. He's also served as a TA for a number of my courses. Just a very multi-talented person and just a wonderful person to work with. Yuki Fan, I'm co-advising her. She is a PhD student in chemistry. Her primary project is on photothermal effects in ceramics, but she's also working together with Maziar on bioactive glasses and bringing a really great, unique perspective coming from her chemistry background to this design of bioactive glasses. Chang Han did his master's degree with Dr. Susan Sinnott at Penn State, focusing on molecular dynamics simulations, and he is pursuing his PhD with me now on a project that is devoted to MD simulations of glass to look at crystal nucleation behavior and the connection between topological fluctuations in glass and nucleation and crystallization. Christina Hunter is a new student who is joining our group, co-advised with Matt Crone from Penn State's Applied Research Laboratory. She is just graduating from Brigham Young University in Boise, and she is going to come to Penn State to work on dielectric glasses. So very excited to welcome her to the group this August. Three students here are actually co-advised with Dr. Song Kim, who is a professor in chemical engineering and my partner in crime on a lot of these glass projects. Song is an amazing expert in glass surface science. He has published a great new textbook with Wiley on surface characterization of materials. Bahara, Mason, and Mehmet are all pursuing their PhDs in chemical engineering, working together with both Song and myself. Bahara is working on zirconia glass ceramics and also partnering closely with Mazier on that. Mason is working on nucleation and crystallization from both a theoretical and experimental point of view and has some really exciting new results to share on that. And Mehmet is working on LionGlass for architectural and hollowware applications. He's also working closely together with Professor Julian Wong in architectural engineering here at Penn State. And they're all doing awesome work. And then the fourth student is Dan Kramer. And Dan is another really special case because he did his bachelor's and master's degrees with Carlo Pantano here at Penn State. We actually hired him at Corning. I was a part of hiring him there. And after a few years at Corning, he went to Vitro in Pittsburgh, where he has been working as a research scientist for the past several years. Vitro is going to send him back to my group here at Penn State to start his PhD this August, and his project is focused on LionGlass for float. So we're going to assess the float compatibility of LionGlass and basically do what we need to do to scale that up. Next is Christian. Christian actually has about 5 years of experience working in the Colombian glass industry, and he's coming back to school to get his PhD, working closely together with Owens Corning on fiberglass and especially glass refractory interactions for fiberglass compositions, doing great work on understanding the chemistry as well as the impact of chemistry on thermodynamics and kinetics of these glass refractory interactions. Adam comes from my neck of the woods. He is originally from Horseheads, New York, did his bachelor's degree from Alfred University and then master's at Penn State, and has stayed on to do his PhD. He's going to be finishing up soon. He's doing a project on infrared transmitting oxide glasses with a particular emphasis on vanadate glasses. He's done a lot of glass melting, glass composition design, characterization, as well as developing topological constraint models for these glasses. Another really multi-talented person, also a really great writer as well. Jessica Sly comes from John McCloy's group at Washington State University, and she started learning about glass corrosion there in the context of nuclear waste glasses, and is really kind of diving in deep to the science of glass corrosion and proper ways to characterize it, and focusing now on borate glasses. And she is looking at this from multiple perspectives, glass chemistry, glass physics, and trying to put a lot of rigor around processes that haven't necessarily had as much rigor as they should. And so her research is very exciting. And also Danchi, who is working on a project for, related to hollow glass microspheres. She is a graduate of Coe College, getting degrees in both physics and mathematics. And she is looking at microspheres from both a physics point of view and a chemistry point of view, and making exciting progress in both theory and experiment. We also have a number of great undergraduate researchers working in our group on various projects. One of the things I love about Penn State, much like Alfred or much like Coe College, is the ability for undergraduates to get great hands-on research experience. And Elizabeth, Julia, Olivia, Allison, Daniel, Nathan, Brendan, and Sophia have all been just wonderful members of the group and have contributed to so many of our different projects there, and they all have very bright futures ahead of them. Now, let me turn the focus of the rest of the presentation over to LionGlass. The problem that we're trying to address here is the carbon footprint of the glass industry. As happy as I am with all of our great work at Corning and developing things like Gorilla Glass and optical fiber and display glasses, the fact remains that the vast majority of the volume of glass that is being produced is still soda lime silicate glass, and this has not changed in a very long time. And so if we want to do something about the carbon footprint of the glass industry, we need to do something about soda lime silicate, and it needs to be a step change away from traditional soda lime. The glass industry itself has kind of put itself into a catch-22 situation because the companies that do have the resources to invest in something like this aren't necessarily interested in getting into a commodity market like this. And the commodity glass companies, simply don't have the profit margins to invest in the type of research that would lead to a step change away from soda lime. So I was, very fortunate with my group here at Penn State that we have the knowledge and the resources and the desire to take a crack at this. And what we're trying to address is the fact that the glass industry produces over 86 million tons of carbon dioxide every year. About 70 to 80% of that is energy consumption due to the high temperatures required for melting, about 1450 degrees C for soda lime. And the other 20 to 30% comes from decomposition of carbonate batch materials. So soda ash and limestone are both carbonates, and when they're melted, they decompose to oxides, releasing CO2 in the process. This latter part here could be addressed by recycling of glass, but that still doesn't help when it comes to energy consumption. So we really need to do something to eliminate the use of carbonate batch materials and significantly lower the melting temperatures if we want to have a big impact on this number. So that's where LionGlass comes in. The name LionGlass actually comes from our dean, Dean Lee Kump. He came up with this name. So I guess this is, in the tradition of like Gorilla Glass, that the best glasses are named after animals, and this is named after Penn State's mascot, the Nittany Lion. So that's where it comes from, Lion Glass. And this, first of all, reduces the melting temperatures by about 400 degrees Celsius compared to standard soda lime silicate. It also eliminates the use of carbonate batch materials. And so, for example, the table here on the top shows the measured amount of gases that are released during the batch to melt conversion process for a 125-gram batch of soda lime. And that leads to over 24 grams of CO2 being emitted just as a result of the carbonate batch materials. Compared to LionGlass, if you see the table on the bottom here, that only has 0.3 milligrams of CO2 that is released as a result of the batch to melt conversion process. And so it is essentially eliminating that part of the CO2 consumption. And then by reducing the melting temperatures by about 400 degrees, this ends up with roughly a 50% decrease in the carbon footprint of glass manufacturing, depending upon, of course, the source of fuel that is used for glass melting. Another exciting feature of LionGlass is the improvement of damage resistance. The upper right plot shows the probability of soda lime silicate glass cracking under a Vickers diamond indenter. The indentation cracking threshold is defined to be the force at which the probability of cracking is 50%. For soda lime silicate, that's about 0.1 kilograms force. LionGlass pushes that up to more than a factor of 10 greater. We maxed out what we could do with our indentation equipment here, going to 1 kilograms force and still only had a 25% probability of cracking. So it is a dramatic improvement of damage resistance. This is something that we were able to do at Corning with some of the newer Gorilla glasses, where it was commercialized as native damage resistance. Here we're getting this improvement without ion exchange. It is a native property of the glass itself, where basically it's able to dissipate energy through kind of a nanoscale plastic deformation rather than dissipating energy by forming cracks. And so as a result, it takes a much larger force to be able to introduce cracks. And so this is advantageous on its own in terms of improving mechanical performance, but you can also trade off this improved mechanical performance to enable lightweighting of glass products. Lightweighting has numerous advantages, including reducing raw material consumption, further reducing the amount of energy that is required to make a glass product, since less material needs to be melted, and lighter weight products reduce the cost and the carbon footprint associated with transportation of the final product. Last thing is that LionGlass, depending upon the exact formulation, because it is a family of glass chemistries, it can also improve UV absorption. So any products that may be subject to UV degradation, like cosmetics, beverages, food, there can be some additional protection from LionGlass. LionGlass can also adopt all the same different the same colors that soda lime can take on based on transition metal or rare earth dopants that are added. So it's also really nice as an artistic medium, and it is meant to be a drop-in replacement everywhere that standard soda lime is used now. So this includes architectural windows, automotive glazing, jars, bottles, tableware, art glass, and in many of these cases, the ability to lightweight these products has additional advantages, cost advantages, and environmental advantages. One of the nice things about working at the university and being able to get some internal support for this is that we were able to file now 3 patent applications on related to LionGlass that covers the broad range of compositional families as well as various applications of LionGlass. And there's no strings attached to any funding agencies or any companies. So this puts Penn State in an enviable position with respect to IP ownership. And so we've been in the process now of identifying industrial partners to work with in different geographical regions and in different market areas to scale this up for industrial manufacturing and to license the technology. The goal is for this to be kind of like what Gatorade is for University of Florida. So this is licensed technology that can bring in royalty revenues for the university, and that money can be used to do good things here, like offer scholarships, especially for students coming from disadvantaged backgrounds, and also to help fund our research enterprise here at Penn State. We've been working together with Celsion, which is this great company that is based in the Netherlands. They do so much nice research related to glass melting and forming. We've been working with them on the melting side. They have this great setup with transparent crucibles and a furnace that has a transparent window where they can actually take videos of the batch to melt conversion process. So you can see these reactions happening as the batch materials are heated up. This furnace is also hooked up to a gas chromatographer that measures the concentrations of gases that are being released during this batch to melt conversion process. This shows a photograph of their setup at Celsion and then an example of a video taken through their process where you can see the fining behavior of a glass. And we looked at this to try to do back-to-back comparisons between a standard soda lime silicate and a LionGlass composition. This slide shows on the left here, this shows the gas chromatography results as a function of temperature as the batch is heated up. And on the right, this shows a movie of the soda lime batch as it's heated up and eventually melted. The current temperature of the movie in degrees C is shown in the upper left part of the movie, so it just hit 1,000 degrees C. And it really does take, getting to that temperature before you can see a lot of these reaction kinetics happening. It's a stepwise process, of course. There's decomposition of carbonates into oxides, reactions of modifier oxides with glass formers to make lower melting temperature eutectics and so on. So stage by stage, we go through this melting process, and you can see the gases that get released here that predominantly is carbon dioxide, CO2. The dark blue is CO2 concentration divided by 100, and if you integrate that curve, you get over 24 grams of CO2 for this 125-gram batch. At higher temperatures, you're going to see the SO2 blisters being released. This is because of sodium sulfate being used as the fining agent. And as we get to 1400 degrees C and a bit above that, you can see this foaming behavior. And then when we get closer to 1500 degrees C, things calm down. And then at that point, we get a nice, well-fined, homogeneous liquid. But it does really take, it does require those high temperatures to get good quality melting in soda lime. Now, if we compare this to LionGlass, this is the same type of setup for LionGlass, the same size batch. You can see the gas chromatography results on the left. First thing to note is that this is the actual CO2 concentration, not divided by 100. You can see that this is staying basically at noise levels. So it's just atmospheric CO2 as well as any trace carbonate impurities that happen to be in the batch materials. But if you integrate all this noise, what you get is 0.3 milligrams of CO2. The major gas that gets released from LionGlass melting is water vapor. This is the water vapor concentration divided by 1,000. If you integrate this, it's something like 8 grams of water vapor that gets released. So we're trading in something that is environmentally harmful, CO2, for something that is environmentally neutral, H2O. This also includes a bit of sodium sulfate as a fining agent, and that's where the SO2 blisters come from. Now, if you look at the movie here on the right, even by the time we got to 800 degrees, you could see some pretty rapid reaction kinetics happening with melting. As we get to 900 degrees, this looks a lot like how soda lime looked at 1400 degrees C. And now as we get to 950 degrees C, the bubbles are coming out and we get a nice homogeneous glass. And in fact, one of the cool things that we're able to do with LionGlass is to push the liquidus temperature below 950 degrees C. And so you can see here that at 1,000 degrees C, it's a really nice quality melt. So we are indeed able to, eliminate CO2 from the batch to melt conversion process by eliminating carbonate batch materials and also lowering the melting temperature to reduce energy costs and the carbon footprint associated with energy. Of course, this is a result of the viscosity curve of LionGlass. These are Maega fits to the log viscosity versus temperature. You can see a couple of soda lime curves here in yellow and red, and then the LionGlass curve in blue, where the entire viscosity curve is shifted to lower temperatures. So it's lowering the melting temperature, lowering the forming temperatures, but it's not giving a steeper viscosity curve, which is good because this means that we can control the forming behavior of the glass. One of the traditional issues with low melting temperature glasses is that the viscosity curves tend to be steeper, meaning a higher fragility, and that's not the case here for LionGlass. And you can compare isocom temperatures here. So melting, the same temperature that's around 1400 for soda lime is like 980 degrees C for LionGlass. Working points get shifted down, softening points get shifted down, and the annealing temperature of LionGlass gets shifted down, although not by as much. It anneals at about 450 degrees Celsius. This shows you some indentation results for LionGlass on top and for soda lime silicate on the bottom. This is 1 kilogram force on the left, 0.5 kilograms force in the middle, 0.1 kilograms force on the right. You can see that for soda lime here, it's cracking even under the lower load of 0.1 kilograms force, and you get really significant cracks at these higher loads. With LionGlass, we don't observe any cracking at any of these loads. That's because it is having some nanoscale like plastic deformation mode that's able to absorb the energy of the indenter without creating new fracture surfaces. So it's a pretty dramatic improvement in its mechanical performance. When it comes to coefficient of thermal expansion, it is kind of centered around the same CTE as soda lime silicate. You can see soda lime here in the brownish color and LionGlass in blue, and they are very similar. Depending upon where you are in the compositional range of LionGlass, you can shift this either up or down. But overall, the CTE is pretty similar to what we get with soda lime, which means that you can also use this for thermal tempering, although the temperatures that are used for tempering would, of course, be lower. This is work that was being done by Christian Roos and his group at Aachen University. They measured the electrical resistivity of molten lime glass and compared to soda lime silicate. You can see that that the resistivity of lime glass is just slightly higher as of at the same temperatures as soda lime. But given that it's in the same ballpark, this means that this is compatible with electrical melting, which of course is important to go to lower carbon glass melting furnace designs. So Lion Glass is compatible with that from both a resistivity point of view, as well as separate studies that we've done looking at the reactivity of molten glass with electrode materials. So we are in a very good place with respect to compatibility with next gen electrical melting furnaces. If you just look at Lion Glass, it looks very similar to soda lime silicate because the index of refraction is actually quite similar. The dispersion is actually slightly less for Lion Glass. You can see that the refractive index is more consistent across the range of wavelengths compared to soda lime. The one thing that you'll note that's different with Lion Glass is that it's actually clearer. And that's because there is less iron contamination in the batch materials, but also Lion Glass colors less for an equivalent amount of iron. So whereas you may get a greenish tint with soda lime and basically have to pay extra to get the low iron version of soda lime, with Lion Glass you get that automatically because it suppresses the coloration. This shows my PhD student, Arun, who is the manager of our glass studio, actually blowing Lion Glass in our glass studio. So this is, I think, a beautiful example of STEAM, where he is using this highly engineered material and demonstrating its properties through art. And because a lot of these properties that are needed for blowing of a glass are also the properties that are needed for industrial glass manufacturing. So to be able to melt it and to form it properly, Aaron was able to show that he could, reheat it multiple times, and we don't have crystallization, we don't have phase separation. He was able to control the viscous flow behavior. He just needed to readjust, or kind of recalibrate himself because the temperatures are so much lower that it's not glowing nearly as much as soda lime silicate. And on the right, this is a Lion Glass flower that was made by Nick, my postdoc, who is also very artistically talented. Lion Glass has been, quite an experience for us. It actually got international press here in a featured article on BBC News on the right. We got to be on TV with the Fox Big Noon kickoff and later on the Big Ten Network. So if you watch any of the Penn State football games on Big Ten Network, you probably saw our research highlight, which is really cool because Penn State football games are viewed by like a million people, and much like Gorilla Glass, that kind of captured the attention of the general public and changed the way that the general public viewed glass. It seems like Lion Glass can is starting to do that as well, which is really cool to see because I would love nothing more than to get more people interested in material science and engineering and more people specifically interested in glass. We also got the opportunity to meet the governor, who's a great guy, maybe a future president, who knows? We'll see, but it's been, quite a ride. We have been working also with our first industrial partner is Bormioli Luigi. They are based in Parma, Italy, and they have been just wonderful partners to work with. Nick, who is here, and Titus, who is here, just got back from Venice, and they made these first ever Lion Glass cups. And they did this in Murano, which was amazing because I think you all know the long history of glass innovation at Murano, and they got to be a part of that history now, taking this next big step forward in glass technology in on this island, outside of Venice that has this really long, amazing history of glass innovation. Bormioli Luigi is a leader in packaging for cosmetics applications, and they are getting a lot of pull from their customers to go to greener packaging. And so we're, really excited to take these next steps with them. This shows a photo from this recent LionGlass trial in Murano, and one of the glasses right here. And there it is. So beautiful job. I'm amazed by the quality that they're able to obtain in a relatively short period of time. So my students are also hard at work on LionGlass for architectural applications in addition to packaging. This is Mehmet, who is working together with Aleph to make some flat pieces of LionGlass and to get good quality. And you can see this beautiful piece of LionGlass that he made over here on the right. So we are characterizing these for architectural applications. We're looking at coating compatibility and so on. When it comes to glasses for architectural application, things that matter include not just the corrosion resistance of the glass, also the thermal conductivity of the glass, and the ability to apply different types of coatings to filter out different parts of the spectrum, because we want to make our buildings as energy efficient as possible. And what we are seeing so far with LionGlass is actually a very consistent performance with respect to soda lime silicate. And so everything actually looks quite encouraging at this point. Aleph is actually leading some of our research on recycling of LionGlass, and we've been working together with our friends at the Penn State Harrisburg campus, especially Bob Bylone here and Pete. They are in charge of the Pennsylvania Recycling Markets Center, which is based at Penn State Harrisburg. And we've been working together with them and with their network to see how LionGlass, how a recycling stream for LionGlass can be set up, and especially with respect to the current soda lime silicate recycling stream. So my group went on tours of multiple recycling centers, including this Balcones Recycling Center in New Jersey. There they are. There's Mehmet and Aleph and Nick. And they got to tour these recycling centers and see their equipment. See, this is some of the glass cullet that is being generated there. And you can see this coming down here in those videos. It's really amazing how it works. But one of the key things that we learned was their use of X-ray fluorescence, such as this equipment by Red Wave. XRF is used to separate out lead silicate from soda lime silicate by detecting the presence or absence of lead. And so Aleph is actually working on generating these X-ray standards that could be adopted by these recycling centers to help sort between LionGlass and soda lime silicate. She has also been working on generating cullet-compatible versions of LionGlass. You can see LionGlass pouring on the left. And then in a moment, you'll see a cullet-compatible version of LionGlass that is meant to be compatible with soda lime cullet. One of the issues is the transition from soda lime to LionGlass is a major transition. And so if we can make use of some soda lime cullet in that process, that would be advantageous. We still have work to do. You can see the LionGlass on the left with its beautiful quality. Cullet compatible version has good quality, but there's still melting issues that need to be addressed. So we are actively working on that while also working on how to best put together the recycling stream for LionGlass itself. So with that, I want to thank you so much for your time. It has been a pleasure working with all of my great students here, and I'm happy to take any questions that you may have. Thank you.